Let's now talk about the second rule for WP calculation. We talk about conditionals or alternations. And as usual, let's give you enough intuition so that you will really appreciate how the rule has been derived. What we're talking about over here is alternation. We got some Boolean condition, which might be true or false at runtime. If it is true, we're going to execute S1. And then if it is false, we're going to execute S2. So you can see to really establish R, we got two cases to handle. Either when B is true, in which case we're going to apply the WP rule for S1. If B is actually false, in that case, we're going to apply for S2. That should also be able to establish R, right? So you can see we got two cases over here. And notice that S1 and S2 over here, they can be arbitrarily complicated. It's really important to realize this. So for S1 and S2 over here, they can be arbitrarily complicated. Arbitrarily complicated. So think about if you're really defining the WP function programmatically. You're going to say WP over here. The first one is simply just going to be S of type program. And the second argument would be simply R of type maybe predicates. This is how you would actually implement a WP function if you want to deal with programmatically. But as far as the course is concerned, we only ask you to really apply that by hands only on the paper. But I'm just trying to give you some context over here. So now for this particular declaration here, for WP function, the program here can be arbitrarily complicated. That's why whenever you program function, you want to think about any arbitrary input that's actually passed to WP. You should be able to handle that, right? So the program here can be assignments, it can be if then else, and also it can be sequential composition, it can also be some loops, right? So these are the four possible inputs that you must be able to handle, right? And also for the predicates, it can also be arbitrarily complicated using the logical combinators, operators. All right, so now let's talk about what the rule should be like if we are given this particular input over here. So this is the input we're given. Let me try to give you some skeleton to start with. We know that we got two possible scenarios to really run into at the runtime. So either when B is true or when B is false. So either when B is actually the case or when the B is not the case. When B is the case, we know that we're going to execute S1. And when B is not the case, we're going to execute S2. And we know that for both cases, the ultimate goal is really to say upon termination for either S1 or S2, we want to establish R. So now we want to know what is the weakest precondition for S1 to establish R. That's something we can calculate. Of course, it depends on the structure for S1. It's a recursive calculation, basically, for the WP, right? That's why I mentioned that in order for you to implement WP, if necessary, you have to think about all the general cases. And also for S2. So we're going to calculate the WP for S2 to establish the same postcondition upon termination. But now, here's the problem over here. How many Boolean conditions do we have? 1, 2, 3, and 4. And what should be the result for this WP calculation? It should be just a single Boolean condition, right? So now what we want to do is somehow we want to combine all these four so that it can become a single Boolean conditions. How do you combine different Boolean conditions into a single one? You have to apply logical operators like a conjunction, disjunction, and implication, right? Let me just tell you what they should be over here, okay? It turns out we should really say when B is true, that implies the WP must be the case. And also when B is not true, it should really imply WP is not the case. Okay, so that's number one. It's about implication. And then how do we combine these two conditions together? We want to say the intuition is we want to say this branch must be able to establish the desired postcondition, and this branch should also be able to establish the postcondition, basically both branches. So that's why we should really use conjunction over here. You might be wondering why over here we should really use implication as opposed to conjunction. And also over here, why we're using conjunction over here as opposed to disjunction, right? Here, why are we not using conjunction? It's a reasonable doubt, but I would say in order for me to really give you more intuition, I would suggest we switch to a concrete example to see exactly why. All right. Let's now go to a concrete example over here. Okay, so basically the question is, you can see this is one alternative. This is the actual rule, right? We can simply say conjunction over here. And then I'll also explain as we go through the concrete example why this should be implication rather than conjunction, right? That's something we'd like to understand very well, okay? And that's the WP problem we're given in this particular case for conditionals. Let's see some very concrete example. So we say this program here, if y is larger than 0, we're going to increment x. Otherwise, we're going to decrement x. And then we want the post condition to be established being x larger than or equal to 0. That's something we'll like to do, right? So now let's see, let's apply what we know already. So case number 1, y larger than 0 should imply the WP for branch number 1. X is assigned to x plus 1 to establish the common post condition here. So x larger than or equal to 0. And we know that both branches must be able to satisfy such constraint. So when y is not larger than 0, you can maybe write this way. It is not the case. Y is larger than 0. That implies the WP for the second branch, which will be to decrement x. So x is assigned to x minus 1 to establish, again, the common post condition here. X larger than or equal to 0. So that's the rule. So now let's think about hypothetically, right? Hypothetically, what if I simply change this part over here to be just conjunction? Let's think about why this would not work. I don't even need to look at this concrete example here. I can just tell you this. You can think about at the runtime, is either this true or this is true, but not both. Agree? All right. So now let's say at the runtime, if y is simply equal to 1, so that means this part over here is going to be true. However, this part over here is going to be false. In that case, false and anything will just be false. So that means this entire thing over here is just going to be false. So false and anything will also be false. So that means the entire thing over here will just be false. So that's why when you simply just use conjunction over here, it's not really doing the case analysis well or appropriately. So whenever you want to say, if I can either go for case number 1 or case number 2. So now case 1 constraint and case 2 constraint should be treated as antecedents. So that's why this should be implication over here. All right. So I already justified why implication over here should be used rather than conjunction. Okay, that's very important. So rather than just getting the diagram to be the page to be too messy, I'm just going to undo. But you can definitely watch the recording part to see why it would be the case that conjunction should not be used. So now it would be important now to justify why we are really using conjunction over here rather than disjunction. So that's something I would like to talk about. So why are we not using disjunction here? Why? Okay, let's think about what's going to happen here. Let's say we talk about a particular runtime scenario where y is equal to 1 and x is equal to minus 4, for example. Okay, so when y is equal to 1, we know that this part over here, y larger than 0, so 1 larger than 0, right? So y is equal to 1. So that means this part here is simply just going to be true. And this part over here, no doubts, is simply just going to be false, right? So it's these two conditions are mutually exclusive, right? So 1 larger than 0, true, and then negation will be false. All right. So now you would see that over here, this will be this part over here. False implies anything. So that means this part here would just be true, trivially, right? And now if you simply say or over here, if you really apply this alternative operator over here, so now true or anything would just be true. So that means this entire thing over here would just be true. Basically always. Because think about, is this really specific to this particular concrete example that you always get true? It's not really specific to this concrete example. It would just be always the case, which is inappropriate because over here, you know that either this condition will be, either this antecedent will be true or this antecedent will be true. Let's say if this antecedent is true, the other one here will be false, and false simply implies anything. Doesn't matter what the particular implementation or postcondition is. This part here, the other branch will just be true, trivially, because we got false antecedents. In that case, if we simply use disjunction, everything here will just be true. So that will actually give us some misleading result, because whenever you get true for your precondition check, so that means your program is correct. But is our program correct in this case? Not really. Okay. So now this true over here, by using disjunction, misleading result. And when I say disjunction over here, I really talk about the alternative that we talk about, right? I just put a question mark here because we're not too sure if that will be also working. For this particular example here, you can see when y is equal to 1, in that case, we're just going to, let's say x is simply -4 at the moment, right? So if you say -4 plus 1, that'll give you -3. -3 larger than or equal to 0 is going to give you false, right? You potentially can run into post-condition violation. And similarly, you can see on the other hand, if you got y is equal, if you got x equals -4, well, of course, this one at the runtime is not going to be executed, so we don't need to talk about it. So it's mainly this part. You can see by executing this particular branch, we can run into some potential post-condition violation. However, simply by using the disjunction over here rather than conjunction, we can simply just get true, just because the false antecedents for the other branch will simply give you true, trivially, and true and true or anything will simply just give you true, trivially. So that's why they'll give you misleading result. Okay, so the conclusion is we shouldn't really use disjunction over here. We should always use conjunction. By using conjunction here, you can see the false over here. So that will actually give us simply just false. Because if you try to apply, think about what's going to happen. If you simply get false, how do you calculate the WP? It's going to be the false over here, and then replace every occurrence of x by x plus 1. There is simply no occurrence of x in false, so that will just be false. So what's going to happen is you're going to have true implies false, right? That the WP part is simply just false. That will just be false. And now false and anything will simply just be false. So now this false over here is going to give us the correct result, because the program is simply not going to be correct, because at least for this particular counter example, it's actually going to give you some potential post-condition violation, right? So that's very important to realize. So this is the correct result by using conjunction over here. All right. So this is really, this page here is not really to give you some new rule, but we want to justify why we should really use conjunction here as opposed to disjunction here. If you simply use disjunction, it's actually going to give you maybe the wrong signal to say the program is actually correct, but in fact it's actually incorrect. Okay, let's go back to the slides. So that's the final rule for the WP calculation for alternations or conditionals, but we explain in detail about why we should always use disjunction over here for case analysis purposes, and also conjunction here to say that both branches must be able to establish the desired postcondition. Okay, you may want to review the parts about explanation which I went over in detail if necessary. All right, so now we want to talk about what will be the proof rules, really. We just talked about how you can calculate WP. Let's now apply this in the context of Hoare triple. Remember, in order to prove the Hoare triple, we have to prove this particular implication, right? The same idea. So now let's say this. If the S over here is simply replaced by the if then else that we spoke about, now how should we do it? Basically, you want to calculate the WP in order for this particular if statements to establish R, and we talked about it already. And then you want to make sure the Q is actually stronger than the whatever WP calculation we made, right? We're gonna end up having. Okay, so now this part over here is just to help you think about how the proof rule will actually work. So we started with the precondition here, And then it's either that we go to one branch, in which case you can see right before we try to execute S1, branch number 1, both the precondition over here is satisfied, and also this B here can also be assumed, right? And then we want to establish the postcondition R. Otherwise, the same precondition will still be assumed, and then we're just going to assume that the not B is the case because we go to the else part, and then the same postcondition must be satisfied, right? And then eventually, we just want to make sure upon termination of this particular if then else statements over here, the postcondition should be established. Okay, so now it's really about these two Hoare triples that we want to prove as two tautologies, but we can combine them together. Let's see. So let's say, again, this is the given Hoare triple. We know that it simply can be boiled down into this Hoare triple and this Hoare triple, right? That's exactly these two over here, number 1 and number 2. And both branches must be correct, both branches. So that's why we're using conjunction over here, right? So we calculate the WP for this, and we calculate the WP for this. So what we're going to get is, you can see WP for S1 to establish R, WP for S2 to establish R. And then what will be the antecedents? And the antecedent will simply be the precondition over here, the same. And then either you go to branch number 1 or you go to branch number 2 by assuming either B or not B. Okay? So that's about the proof rule. You should really keep in mind. Of course, you don't necessarily have to memorize the rule. It's going to be open test later. In that case, you can always have this rule handy. However, you want to be very clear about why we're using implication here and why we're using conjunction over here. That's important. The only exercise we have now, actually, when I actually justify this particular rule, I already show you how you can apply the WP over here, right? So I don't need to repeat that application process. I'll leave that to you. So what I would like to do is, I just want to show you quickly what the answer is, and then there is still something that we cannot do just yet. Because you can see for this particular program, assuming that x is larger than 0 and y larger than 0, we want to establish bigger, larger than, or equal to smaller. So you can take a look at that to see what a program really does. It's basically just doing some proper discovery of the maximum and the minimum between the two numbers. And then we say either x larger than y, or it's not the case that x larger than y, meaning that x is smaller than or equal to y. And we're going to do this followed by this. We haven't spoken about the WP rule for the sequential composition. We'll do that in the next video, but let me just to see what we can do so far. So what you're going to do is, you can see you have this particular precondition, which is x larger than 0, y larger than 0, right? That's a precondition. And then we got this branch number 1, which is x larger than y, right? We include it here. And then, in that case, we're going to execute the implementation over here, and then we're going to establish bigger, larger than, or equal to smaller, right? So that'll be the first one. We want to make sure the first branch will be correct, and the second branch is also correct. That's why we're using conjunction. And then here, what about the second one? For the second one, we still have the same precondition over here. It's common to both branches. And then, for the second branch, the Boolean condition here is simply false. That's why we get into else. So that's why it's a negation over here. And then the implementation is simply going to be exactly this guy over here, right? We're just going to do different implementation depending on the branches. And what about the post condition? The post condition will just be the same. Bigger, larger than, or equal to smaller, right? We cannot really go any further simply because we don't really know how to really calculate the WP. For this particular implementation, because in order to prove that this particular Hoare triple is actually a tautology, we have to calculate the WP for this program to establish this post condition. However, this program over here contains sequential composition, which we don't know how to proceed. So I would say our pause over here, just for this particular example, once we know about how to calculate the WP for sequential composition as an exercise, which I highly encourage you to come back to actually complete this particular proof. All right, so that will be about the WP rule for alternation or conditionals. Okay. You may want to stop the video now, and if there's anything that's not clear to you about how to apply this rule, or what's the rationale behind the rule, you may want to revisit certain parts of this video once more before you get to the next one.